Welcome to After Hours Engineering, episode 14. In this episode, we travel the outskirts of the world of control and status registers, or CSRs. Why only the outskirts? Because CSRs encompass a huge range of capabilities and functionalities. For example, identification, such as the machine ID, counters like cycles and retired instructions, addresses like trap vectors, mode bits like user, supervisor, and machine mode, of which we're only doing machine mode in this one, IRQ bits, which we'll talk about later in another episode, values like cause, which we won't be using, statuses we'll definitely use, that'll tell us whether an interrupt or what state the processor's in, delegation, and buffers, like scratch buffers. We won't be using those either. There's very few we're going to use, but there are up to 4,000 for sure, if you have room to spare. This makes the topic much too large to tackle in this series. It just won't do it justice. And as such, we're only going to cover a tiny subset of the registers. And by tiny, I mean only 5. So let's take a look, shall we? To start with, one of the main things to understand with CSRs is that some of them could actually be hardware. For example, an LED or a shift register or even a switch for that matter. The idea here is that implies that many of them come with a possible side effect, either when reading or writing from them. Let's say in your design you have a CSR that is a hardware read and write shift register. It's actual hardware. It's not a LUT or anything like that or a flip-flop. It's physically a shift register. And every time you read from the CSR, it resets to 0. Perhaps that's what the manufacturer has on their shift register. This reset is a side effect, and there can be a large number of them. However, to keep our design simple and intuitive, we will severely limit the number and functionality of our CSRs. For example, out of the 3 possible modes, we're only going to implement the M mode, which reduces considerably the number of predefined CSRs. All registers are read and write, which is different than what the specification says. The spec says that they could be registers that read only, write only, or read write, but we're only going to do read write. Our registers will be fully accessible in all manners. And this eliminates access circuitry and privilege checks in this case. Also, we're only going to implement 5 registers: the M status, the MIE, the MIP, the MEPC, and the MTVEC, or in this case, the direct mode version of MTVEC. So why only 5 registers? Because in this series, our interest in CSRs only extends to interrupts. And this is because we'll need interrupts when we implement a simple parallel I/O protocol, which we'll cover in a later episode. So let's start with the M status register first. The M status register contains 2 bits of interest, the MIE and the MPIE. These are the bits that focus on M mode level interrupts. MIE is the global interrupt enable bit. If it's 0, then all interrupts are disabled. MPIE is the previous enable bit that is typically restored at the end of a trap handler. All other bits are ignored as they pertain to modes and ISA extensions that we are not implementing. Also, if we are only using 2 bits, do we really need to define a 32-bit register? The answer is yes, and its size is defined by the MISA MXL field. Because we're using the Ranger RISC RV32i variant, then MXL is always 1, which means that all of our CSRs are 32 bits. And so we will not implement that register because that value is always 1. Next is the MIE and MIP registers. Together they are mirrors of each other, where each has a single bit we're interested in. The MIP register has the MEIP bit, which is typically driven by an external signal. This signal can be sourced by an interrupt controller. However, for our simple design, it's a directly controlled signal. This bit represents a pending interrupt. So if an external device wants to signal our processor, they will set this bit, and then our processor will see it as pending and eventually process it at the end of an instruction or the retirement of an instruction. The MIE register has the M mode MEIE enablement bit for interrupts. Just like the global one, if it's 0, then M mode interrupts are disabled. The MEPC register holds the return address of the next instruction just after a retired instruction. It's used by the machine return system instruction for resuming program execution. It's populated at the end of an instruction if and only if the interrupt pending bit is set. Our implementation is fairly simple in that we will always assume that the I-align value is 32, and as such we set the lower two bits to 0 when reading the register. You can think of this as a side effect in and of itself. Finally, the MTVEC register holds the address of the trap handler or interrupt handler. The lower two bits specify the mode. Our design uses the direct mode rather than the base mode, and as such, our value that's in this register is the literal address of the trap handler itself. This register's value is loaded during the boot program, which is executed before any other code executes in and of itself. We'll see this later when we set up some example machine code to test out the interrupt handling routines. Now we look at the instructions that directly impact the CSRs. All 7 have the potential to cause side effects, and these are the CSRRW and its matching immediate version, the CSRRS and C and their matching immediate versions, and then finally the machine return instruction. We'll look at the explicit CSR instructions first, starting with the CSRRW and its equivalent immediate. There are 2 data flows that can happen depending on the destination register file. Over here to the left, the destination is X0. If that's the case, there's only one possible side effect that can happen, and that's writing the RSA into the CSR register. That's it. There's no reading that goes on. On the other instance is when the RD is not equal to X0. In this case, the RD is X2, and as such, we'll do all the data flow paths in it. We'll have both the write side effect and the read side effect that occurs. Step 1 is to capture the RS1 into RSA. 2 would be to copy the CSR into the destination register. And then finally, take the RSA and move it into the CSR register. That's your 2 data flows with the CSR. That's what the CSR RW instruction does. For the CSR RS and RC instructions, there are 4 data flows that can happen depending on not the destination but the source register file. So if we take a look, in case number 1, if the source register is actually the X0 register, then the only thing we do is read from the CSR, and which produces only a read side effect, and the value is thrown away. However, if the RS1 is actually a 0 value and not the X0 register, then we effectively are doing a circular read and write. We read from the CSR and then turn right around and write it back in. Now this is just a logical representation of the RS1 value. It really is either one of these instructions. So let's look at the set version first. The way it works is you have your source register, which is sourcing a mask, and for every bit that's a 1 in there, we're going to set the corresponding bit in the CSR. So logically, that is taking the mask and ORing it with the data that was in the CSR and then writing it right in. So it's again a 3-step process. We're going to capture RS1 into RSA. We're going to grab a copy of the CSR before the algorithm is applied and store it in the destination register. And then finally we'll run the algorithm on the register itself using the OR Boolean operation here. That's for a set. For a clear, it's almost identical except that the operation is a NOT with an AND gate. Again, RS1 is supplying a mask, and for every bit that's a 1 in RS1, we actually clear a bit in the CSR register. For example, if this bit coming in is a 1, that's a 0, and a 0 on an AND gate is a 0 coming out. So it's exactly the same on the left. There's the three-step process. We copy RS1 into RSA, we back up CSR into RD, and then we apply the algorithm to clear any of the bits. And that's ultimately what the CSR, RS, and RC instructions do in terms of what they logically do. Now, how we implement that in HDL is what we'll look at coming up in another episode. Awesome. We now have a rough idea of what CSRs are and how we can use them to interact with interrupts, and what side effects occur when reading from or writing to them. In the next episode, we'll implement these instructions and we'll write some machine code. So until next time, peace.